Good evening, everybody.
Good evening.
Yeah, welcome you all for today's lecture. I'm Kamala Gunwardana, fellow representative of this session, and I'm chairing the knowledge sharing subcommittee of Civil Engineering Sectional Committee. So before I start today's program, I would like to request you all to mute your microphones all the time, except when you have to ask a question. Thank you for that. You all are now very familiar about these activities of Civil Engineering Sectional Committee, and your participation for all these presentations, webinars and all I actually highly appreciate, and it's very remarkable, and that itself an appreciation for us, for our work. So, and in return, we too appreciate this support. As you all know, today's webinar is a continuation of the previous title, Structural Forms for Tall Buildings, and this medium rise building designs and constructions. It is done by our Professor Jayasinghe, and this is the 8th lecture from this series. So we can start the lecture today, right now, but I think Professor will join soon.
I have joined. I have joined.
Okay, yeah. So today's start in this one, and I'll call upon our eminent personality of Professor Jayasinghe. And actually, he has taken the full responsibility, and he's shouldering, sharing this knowledge about this side of designs and construction of medium rise buildings. So we were very grateful for that. Without further ado, I call over Professor Tishan Jayasinghe, Senior Professor of Civil Engineering at the University of Moratuwa, as well as our Chairman of the Civil Engineering Sectional Committee, to proceed with the lecture. Please enjoy this evening with this webinar. Thank you, everybody.
Thank you, Engineer Kamala. Can you all see that PowerPoint presentation?
Yeah, okay.
Yes, we can. Yeah, you can. Good. Yeah. So last time I gave an introduction. I told you, the various general stuff, like, what the type of concretes that we'll have to use. And then we also talked about the deflection and drift index, wind-induced movements. We'll be covering these in great detail later. But what I wanted to emphasize was, in a tall building, the lateral load resistance system can be very important. And in addition to that, we need to have an efficient vertical load resistance system. So once you have both systems, we need a good foundation. A foundation that will not move, because we don't like buildings moving at the foundation level. We like buildings to be stationary. So basically, we are talking about vertical cantilevers. Generally, when we are talking about cantilevers, we always think about horizontal cantilevers. Something projecting out without a support is a cantilever. So all the tall buildings are vertical cantilevers, where if it is a cantilever, then we must fix it at the foundation level. If it is a cantilever, we must fix it at the foundation level. So we have to see how we fix it at the foundation level. And for that, I have separate presentations on how to deal with raft foundations, how to deal with pile foundations, and even in the raft foundations, whether you want to have a solid raft or a cellular raft or inverted T-type raft, where we'll use the inverted T's plus the confined soil, the soil confined by the ground slab to act like a raft. And then we can also have raft foundations on sandy soil or laterite soil, And in the laterite soil, we might find sometimes the water table is high, sometimes the water table is low. So I'll show you that the modeling techniques can be very different when the water table is high and water table is low. The reason is, if the water table is low, we have laterite soil, we consider soil behaves like a sand. On the other hand, we have laterite soil, water table is high, then we consider the soil behaves as a clay soil. So clay soils are very different to sandy soils. So if they are different, then we will find the modeling methods can be very different. So these are very fine points, and I will highlight all those points, as the time, as we master this subject more and more. Because those are complicated things. So we'll start with simple things like structural forms, but we'll go deep into the structural forms. The reason is, the moment you go deep into the structural forms, you will be able to appreciate the behavior of a building without designing it. So when an architect comes up with a building and they will say, this is the core, this is the form, then when they say that, you would say, okay, I can see that, according to the layouts that you have given, I can make use of this type of structural form, but unfortunately your building is too tall for that type of structural system to be successful. Because of that reason, we have had so many additional things to make it successful. And for that, you have to allow us some machine flows at certain levels or something like that. So you can continue the discussion. And the moment you start the discussion in this fashion, where you give reasons for your decisions, rather than saying, okay, I'll give a try, but rather than doing that, you look at the architectural layout at each floor level, and then you will work out where you can have strong elements that can carry lateral loads. And then you will see whether those can be sufficient or insufficient. If they are insufficient, then you will start explaining the architect due to certain reasons. And these are the reasons, and because of those reasons, I cannot simply use the layout you are given. I need certain additional components. The moment you say that, the architect will think, okay, I have come to the real structural engineer who knows the subject. And then you will start seeing, whether you have to use normal strength concrete or whether you have to go with high strength concrete. And last time I told you, the difference between normal strength concrete and high strength concrete is the elastic modulus. The moment you go with high strength concrete, sometimes you don't need that high strength concrete to carry vertical loads, not even lateral loads, but to control the deflection, sometimes you might use high strength concrete in columns. So there are so many different things that you have to understand. And the moment you start understanding those things well, then without designing, you might be able to give reasons for certain requirements. And that way, rather than wasting your own lot of time to work out refined solutions, you can say, you can arrive at something that's going to work easily. So that's why we are going to look at structural forms today separately. Before doing any calculation, now we are going to understand how a structure can behave. For that, I told you, we can have apartment buildings, hotel buildings, the office buildings, so many different types of buildings are there. So we have to see what are the different structural forms that can be used. And you can see there's a long list of structural forms, and you should have a thorough understanding the behavior of each and every one, so that you will be able to give reasons. So because of that reason, sometimes we might be able to cover all these things today, or if we can't cover, we'll go to another day and cover it, because a deep understanding on the behavior of each and every structural form is very important for you to come up with a good solution. for the lateral load carrying system of a tall building. So first we'll start with the simplest possible structural form. The reason is, this is particularly suitable for steel structures. Then you'll ask why steel structures there, because last time I told you, steel is a good material, but it's not the best material. Why? Steel elastic modulus does not change when you change the strength of steel. Whereas elastic modulus of concrete increases as the concrete strength increases. But when people started constructing early days, they did not have concrete. They did not have, they had concrete, but very weak concrete, like 20 megapascal concrete, maximum of 25 megapascal concrete, nothing more than that in 28 days. But what you have to keep in mind is, those days, I told you the other day, the cement composition was very different. The cement composition was tricalcium aluminate, which gives the strength up to the 14th day, had about only 50%, and 25% was dicalcium silicate, which can give strength from 14 days onwards. So dicalcium silicate was 25%, means, if you cast a concrete and you have favorable conditions where you have moisture, like high humidity, then it will continue to gain strength. And in 1985, I was doing my industrial training. 1985. So how many years ago? 37 years ago, or 36 or 37 years ago, I was doing my industrial training at Labugama Kaltoa Rehabilitation Project. And I was at Labugama, and those days, the facilities were very poor, so no water board engineer ever wanted to serve at Labugama Kaltoa because those were very remote locations those days. But today things have changed a lot. Now almost, the areas like Kottawa has become areas like Colombo, because all the highway system starts there. So, and the railways are there, the broad gauge. So there are so many things happening in this area. So if you are living in these areas, then you'll find your accessibility is very high, because to go to Colombo, you have buses and trains. But to go to anywhere else in Sri Lanka, you have a good highway network. So today, things are changing very fast, and you might find it in 5 years' time, it would be far easier to sell an apartment in Kottawa Homagam area than selling an apartment in Nugegoda. And you'll ask why. If you are living in Nugegoda, it will take 1 hour to go to Colombo and 1 hour to come to the highway. If you are living in Kottawa Homagam area, you will find the train services there. With less than 1 hour, you can go to Colombo. But if you want to have accessibility for the rest of Sri Lanka, then within 5-10 minutes, you can access, you can enter a highway. The moment you enter the highway, the moment we have the missing link of Kadawatha Mirigama, you'll find whole of Sri Lanka is readily accessible. And in 2 years' time, it will be over. Stage 1 will be over. Stage 1 of Central Express will be over. And the same time, Potuhera Galagedara link will also be over. So in 2 years' time, you'll find you can go to Kandy in 1.5 hours from areas like Kottaba, and you can go to Khataragam in 2 hours, 2.5 hours. And you can also go to Anuradhapura in 2.5 hours. And you can go to Kandy in 1.5 hours. But if you are in Colombo, you will take 2.5 hours, because from Colombo to get to the highway link, you will need more time. So because of that reason, there's a chance that we might see a shift in our capital towards Homagama, Kasbah, all those areas, and Kadawatha, all those suburban areas might become our main capital. The most sought after areas might be in 5 to 10 years' time, may not be Colombo, but away from Colombo might be the locations where everybody will be looking for. constructing very tall buildings with apartments and all the facilities, and with that, the chances are we'll get more and more uh, schools and other facilities, because these days you don't need banks, you don't need post office, and you don't need many things. What you need is internet, good data, and a place to live. The moment you have that, you can simply do almost everything you like to do. So the world is changing very fast. So then what you need is accessibility to airports and to the major cities remote from Colombo. And for that, the ideal locations would be the places where you have highway entrance to the highway, and that would be the key. So you might think, you know, where things are going to change a lot in the next 5 to 10 years. And with that change, what are you going to see? We'll see so many apartment buildings coming up in these areas. And that will be the challenge you'll get. With that, you'll get employment opportunities, design opportunities, construction opportunities, project management opportunities. So many opportunities will come. And still our urban migration has not stopped. Still, we don't have more than 45 to 50% of the people living in urban centers, but the chances are the urban migration will continue, and we might have 65 to 70% of the people living in cities. And in those, you will find, you know, the highway interchanges will be the key hubs, and all those hubs will have so many tall buildings, because there's no way we can operate horizontally. Always we have to move vertically. So we'll have great challenges in future, and to meet those challenges, we cannot be using the traditional construction methods and techniques, because traditional methods like reinforced concrete buildings take a lot of time for construction, because first we have to construct the columns, then we have to construct beams and slabs. For that, we have to erect shuttering. So whatever the shuttering system that you use, it takes a lot of time. So then you have to construct partitions. So you think of block work, brick work. You have to carry all these heavy materials over the full building. So all those things will start changing, or will need change, because these are very time consuming and labor intensive tasks. And also you need so many operations to make it work. For example, when you do reinforced concrete slab, first you have to do the shuttering, then fixing of reinforcement, then concreting. After that, you will do a cement rendering. On top of that, you will do tiling. And before doing tiling, you will do partitions. And when you have partitions, you have to cut all the tiles to suit the partitions. So much trouble. And it takes so much time. But on the other hand, you might think of simpler construction, for example, where you will cast only the columns and beams, and today you cast the beam, tomorrow you place some precast beams on the beam you have already cast. And if you can have precast shuttering or temporary shuttering, place it on the beams or hang from the beams. No proper shuttering. All the shuttering is from the beams and precast beams, and you attend to whatever the wiring or any other requirement, and next moment you concrete it, or sometimes not even concrete it. You might consider using some material like straw panels that can be replaced any time, but straw panels have a lifespan of 100 years. These precast beams will have a lifespan of 200, 300 years. So why not repair and replace floor if the floor is made out of straw? And you know, we have a very strong straw panel manufactured in Sri Lanka. We call it Dura, and you'll find that another alternative system is go for precast systems, where you don't pour concrete at all, because concrete is expensive these days. Sand is very expensive, and you have to go for manufactured sand to make it cheaper. But even the manufactured sand is now becoming expensive. And cement is in short supply. So why do we need cement for a concrete floor if we can actually have an alternative made out of natural materials like straw? Because every year we produce so much straw. And if we put some of those straw into our buildings, and if we can come up with good systems that are in par with concrete floors, then you'll find that we can save a lot of time and we can save a lot of money, and also we can make the buildings, apartments affordable. So what is the biggest problem today? Most of you are maybe well paid, but still, even you will not consider buying an apartment. And what is the reason? Apartments are so expensive. Every square foot is sold between 30 to 40,000 rupees. And at that rate, to buy 1,000 square foot apartment having 3 bedrooms and 2 bathrooms, you have to spend 30 to 40 million rupees. And most of the people will find they have to pay huge bank loans for a long period of time if they go for that kind of apartments. And can't we make it 20,000 rupees a square foot with new technology? And that's where the challenge lies. So what we have to say is we need a lot of research done in universities. We need people who are brave enough to adopt these things. But unfortunately, what happens today is all the construction materials, systems, everything is determined by whom? A very uneducated marketing team. Marketing team says, okay, if I am to sell an apartment, it can't have block work, it must have brick. The marketing team might say, you must have reinforced concrete steps if you are to sell it. Then what happens? The engineer says, oh, I like to use the new system, but unfortunately, marketing team is saying they cannot sell unless I comply with their specification. And who are they? They don't know anything about civil engineering, but they are dictating terms to the civil engineers. So my question is, let's say market price for any properly constructed apartment is 30,000 rupees per square foot. Let's say we constructed something with different materials but the same performance. One way or the other, we match the performance. And we say, I'm going to sell it for 20,000 rupees per square foot. If you're going to say it, do you need a marketing team to market? What is the answer? If all the people are selling at 30,000, you make a product which looks the same, and you give a 50-year guarantee on your product because you are sure that it's going to work. And then you say, I'm selling at 20,000. Do you need a marketing team to sell? Manjula, what do you think? If you are selling at 2/3 the price, do you need a strong marketing team? Or you need only few advertisements where people come and grab your product? What do you think, Manjula? So I say it depends, but we should be brave enough to take our decisions and not to be dictated by uneducated marketing teams. They know market research, but market research is based on data. Then who provides the data? Data is again provided by the people. And what the people know? What the people know is only about the product that is available. So how do you convince somebody that you have a product out of different materials, but the performance is same? How do you do that? You'll go for something called display house. So before constructing the actual one, you will construct something exactly the same as what you are going to sell using your new techniques. And then you will bring people, make it display. People come in numbers because you are marketing it at 2/3 the price. And then you do market survey with these people to see what they think about your house. And if they are all happy with the finishers, because what they say is only the finishers finally, and your finishers are exactly same as the finishers in any other expensive house. And
40 second lane po.
And you are giving a guarantee on your product, what will happen?
How
Then
much?
you'll find
Huh?
you need not be dictated by a marketing team who are working on all data. Instead, you will start creating new data using your display. So these are the strategies that have been adopted by the developers in countries like Australia. And I was in Australia in 2003, and I was associated with a huge development in Brisbane, and it was some 35 kilometers from Brisbane called Spring Hills, and they started selling lands at very cheap prices. And those days you could have bought a house in those places for something like 50 to 60,000 Australian dollars, because the land prices were very low. And when I went to Australia in 2018, I visited these places. It was all different. But now two things have happened. One, now there's a railway line connecting Springfields to Brisbane. So people can travel from Springfields to Brisbane town in less than 30 minutes. Number one. Number two, a lot of people have found it appreciates very much. So because of that, they have bought houses in Springfield. So now Springfield is a completely different place. When I went there in 2003, it was all, bare land, few houses. Now today it's a completely different, well-developed housing scheme, a massive housing scheme, having about 20,000 or 30,000 houses. A lot of people in Brisbane, working in Brisbane, are living in Springfields, and it's considered as one of the most sought after places. And then you'll ask why I took this example. The example is, it was considered as a green project. So they allowed a lot of new systems, new materials, and all the companies constructed display houses and then did it. And then there's another importance for that. The person who has actually floated this idea of a massive development was born in Sri Lanka. And I think he was born in Jaffna. And then he migrated to Australia. Now he's a very successful businessman there. And he developed this idea. And those days we also, had a lot of discussions, and we had a lot of research going on with them. So when I was in Brisbane, Queensland University of Technology. So what you have to see is, always think positively and think about new systems that can reduce the need for traditional materials and methods. So to do all these things, you again need to have deep understanding on the structural forms and how they are going to behave. So today, first we'll look at steel, and the reason for steel is we started constructing tall buildings by using steel. So if you have steel, how do you take lateral loads? So if you want to take lateral loads, for example, if you want to take vertical loads, you can have a truss, a cantilever truss. A truss cantilevering from an abutment can carry vertical loads. So if you want to have horizontal loads on a vertical structure, then you need to have a truss, again in the vertical direction. And here you can see what you have is a truss. What you have is a truss. The moment you apply loads, the loads can be resisted, and finally the loads will be transferred onto the connection with the foundation. So just look at it as a truss in the vertical direction, and if you can't understand it properly, look at a cantilever truss in the horizontal direction and apply loads, analyze it, get some idea, analyze it by using a simple program like SAP 2000. SAP 2000 is a very sophisticated general purpose package, but very simple to work. You can understand, wow, it has no black boxes. But so that's why, it's so important that you start with SAP 2000, then start learning ETABS after that, because ETABS has so many black boxes. There are so many, ETABS can do so many things without your knowledge. And so unless you are aware what is going on, you can get wrong results. And we call it garbage in, garbage out. You give wrong data, you get wrong output. So to understand whether you are doing the right thing or the wrong thing, first start with a general purpose package. If you have not done much modeling, always start with a general purpose package like SAP 2000, because it does not allow you any simplifications. It simply give you the basic stuff, and you have to develop your own model from the scratch. And you don't have any black boxes that will do some specified things automatically. In SAP 2000, you have to do it. You have to think and get everything done on your own. The moment you learn the art of using SAP, then no harm in going for ETABS, because then you can understand how the black boxes in ETABS works. Then it's so easy for you to make good models which are accurate. And then, if you can also use MIDAS, and I think now we have made it accessible, but there are so many complaints that, now people are using these 3-month versions for commercial use. So please don't do that, because this package is for you to look for the future, but it's given free for a 3-month period to help you to learn it. So don't misuse it. So the moment you misuse it, we find it difficult to provide you all these facilities. So just use it. Don't use it for commercial purposes. For commercial purposes, most of the people are having licenses for ETABS and SAP 2000. So use those packages, but try and learn MIDAS, because MIDAS can produce calculations for Eurocode. And if you want to automatically generate calculations for Eurocode, so that you just have to review the calculations rather than writing all the calculations, then MIDAS can help you a lot. So learn the good things about MIDAS, and if you think you want to use it, you can buy the license for your company, or you can ask, if you are working for a government agency, you can ask your bosses to buy ETABS for your office, so that you will be able to make use of the knowledge you gain through IESL support for your wealth creation. So that's how you have to look at it. So don't use this package that we have provided free of charge as a trial for commercial purposes. Always use it for educational purposes. Otherwise, we can't convince them to give you all these facilities, because we have a good relationship with all of them. The reason is many universities, we are using it as the key teaching tool, and we pay a lot of money every year to keep the licenses going. And our expectation is you will all learn it, but don't misuse it. Don't misuse it. Now, right, so we look at lateral assistance is provided by diagonal members that act together with main members. Diagonal members form web members of the vertical truss. Columns act as chords. So basically, it's a vertical truss. And one of the main disadvantage of bracing is those can be in conflict with the location of doors and windows. So you cannot freely provide doors and windows because there are diagonals everywhere. So the bracings are usually arranged around the lift shafts and stairways. But the problem of arranging the bracings around the lift shafts and stairways, the size of the trusses can be small. If it is a tall building, you might find the lateral stability is provided by the bracings, but the deflections are too much. The movements are too much. The accelerations are too much. So you can have enormous systems can be weak. So you can have problems. So because of that reason, then people have developed heavy mega trusses. The truss outside the building, you make it a feature of the building. And because it's a feature of the building, what happens? You can see the truss from outside. So you can see it's a steel building. So the architect has to come up with some kind of window system where he will hide the truss as much as possible, or he will come up with a feature where he will show the truss readily so that it can be seen, but he makes his architectural features. So whatever it is, there are so many steel buildings in the world, and most of the tall steel buildings are in America, because they were very fond of using steel buildings, tall steel buildings. But even in America, now the trend is changing, because now they are finding concrete, which is based on natural materials, can be made super strong, and the codes also allow us to use super strong materials. So concrete is very fast gaining popularity. Now let's see the behavior of a truss. The truss can behave in two modes. One is the cantilever mode. The other one is the shear mode. This is shear mode, this is a cantilever. So the difference between cantilever mode and shear mode is cantilever mode, curvature is 0 at the bottom, curvature is maximum at the top. Shear mode, curvature is maximum at the bottom, curvature is 0 at the top. So what is the combined behavior? Combined behavior is at the bottom, cantilever mode dominates, at the top, shear mode dominates. So it goes in one direction, after that it comes back. So it goes in this direction, then it comes back. So that is the behavior that you can expect in a truss. And generally in a horizontal truss, we expect one behavior, and that behavior is maximum deflection at the end. Here also you get the maximum deflection, but in a normal horizontal truss, you will primarily get the cantilever behavior. But in buildings, because there are other frames, you will find that the combined behavior can be one which is dominated by cantilever behavior at the bottom, and then again dominated by the shear behavior at the top. So always keep in mind this happens because there are so many other frames in the structure, and those frames also contribute to a certain extent, and because of that reason you can get both cantilever mode and shear mode. Is that clear, Manjula?
I think, yeah.
They are muted here. Okay.
Yes.
So basically, I will not go through each and every slide, and you can read the slide. So basically, the effects of columns and chords, and then what happens due to web members, which are the diagonal members, and then how the deflected shape occurs as a combination of two different modes, because at the bottom, the cantilever mode dominates, at the top, shear mode dominates. So it's neither cantilever nor shear, but it's a combination. Right. So basically, if you have a large enough shear holes, you can go up to about 50 floors with this system. So rigid frame structures. So these are about rigid frame structures. Now we are talking about concrete structures. Because making a rigid joint in a steel structure is very difficult. But making a rigid joint in a concrete structure is very easy because we are going to cast it at the site. Cast it at the site, easy to cast. So when you in situ cast beams and columns with continuation of reinforcement, what will happen? What is the type of joint you get? You get a rigid joint, a properly connected joint. Before the rotation of the joint, the angle between two members is 90 degrees. After the rotation of the members, still you find angle between two members is 90 degrees. And that type of joint is called rigid joints. Rigid joints. So what deforms is the beam and the column, but not the joint. Joint remains as 90 degrees before and after the deformation. Can you see the definition? The definition is before and after the deformation, joint angle is 90 degrees, but you can have deformations in columns, you can have deformations in beams. So we are having moment resisting connections, and if you have moment resisting connections, you need continuation of reinforcement and also sufficient rigidity generated by having sufficient shear links, so that even after an earthquake, still you'll find the rigid frame action remains. So what will happen if the rigid frame action disintegrate, or you lose it during an earthquake? What could happen in a structure with rigid frame structure? It can collapse. So it's very important. If you are using this system, adoption of earthquake details is very important. If you are in a zone which can be considered as earthquake prone. But in Sri Lanka, we are lucky. But the last earthquake of significant magnitude occurred in 1614 on 14th of April, so nearly over 400 years ago. And that was a very severe earthquake. And I'm sure some of you would have heard about it. Some wouldn't have any clue. So what actually happened was there was a huge cloud of smoke that was emitted by the fault that generated this earthquake. And that cloud covered the setting sun. So around 4 o'clock, it became all very dark. All very dark. And the birds that was flying in the sky, caught up in the dust cloud, died. And they would have died due to the dust or due to some poisonous gas that was emitted. So we really don't know because it happened 400 years ago. But these are all written accounts of the people who have seen the earthquake. And those days, people who saw the earthquake wrote what they saw. And these records are available in our National Archives. So even today, we can get a reasonable idea of what happened 400 years ago. So then what happened was the earthquake actually happened. It damaged part of Colombo Fort, built by Portuguese. And then it also caused the collapse of about 2,000 houses, and it killed about 200 people. Or it can be 2,000 killed and 200 houses damaged. So I can't remember which one is which, but I think more houses are about 2,000 houses damaged and about 200 people killed, because you go in an earthquake unless you have been inside a building. There's no way you can die, because generally the trees will not be affected by an earthquake. So only the people in buildings, within buildings, stay within buildings will suffer. Then the people, the Portuguese, recorded this earthquake. These records are also available. They said, in this country, people are very prosperous and they are very proud. They have plenty of things to eat. Very nice country. And because they are proud, they have been punished by the God. And God's way of punishing these proud people is having an earthquake. And these are all written records. So basically, that gives us another good idea. That is, those days, in this country, we had a good civilization, and those people lived independently. They had their own houses, they were cultivating, they were planting cash crops, and they were having a lot of wealth, and they lived happy. That's what you can gather from all those different writings about this particular. But what you have to keep in mind is that gives us a good lesson. The lesson is we should not rule out earthquakes. We should consider earthquakes, but it's a very remote event. But with high strength materials, we are not talking about structures that can last 50 years or 100 years. Now we are starting to think about structures that can easily last 200, 300, 400 years, which can be refurbished and used. Because concrete is in very good condition, because we are using different additives like fly ash, which will allow us to continuously gain strength, and we are using high strength concrete with low amount of cement, because we are using very low water cement ratios. By lowering the water cement ratio, we can create high strength concrete, and by adding fly ash, we can create high strength concrete. But these strengths may not be available at 28 days, and again Eurocode allow you to specify, I need only 30 megapascal in 28 days, but I like to see something like 45 megapascal in 90 days. Then you'll ask why. The reason is, when you look for longer duration, you are thinking about loads that will come after some time. So you'll ask, why 90 days? Then I will say, are you going to construct the structure in 28 days? No. We might have 30-story, 40-story building. What are the chances that you will complete the building in less than 90 days? There is a chance. So if you are not going to construct the building in 90 days, within 90 days, why do you need very high strength at 28 days? That's a good question. So, but unfortunately, British courts will not allow you to have all these strengths specified at longer durations. But Euro codes allow you to specify anything you like, because it gives strengths, equations for strength development and so on. On the other hand, you can also do it by using set of laboratory experiments. Or on the other hand, you can go to a local manufacturer of admixtures, like Ravi, Mr. Ravi, Millennium Technologies, Ravi Nissank. Mr. Ravi Nissank is very good in helping you with concrete technology, because he has nearly 30 years of experience helping the industry by manufacturing his own admixtures and doing so much, so many cube testing, so that he has wealth of knowledge. And if you are not sure, always consult a person like Mr. Ravi Nissank, provided that you are going to use his admixtures. He will certainly help you to solve all your problems, because he has enormous knowledge on this subject. And if you like, I can actually get him to do one lecture on concrete technology with admixtures for you. Engineer Kamala, what do you think?
Admixtures, we have to be very careful.
Yeah. So basically, we give Mr. Avini Sankar a chance to do a lecture. One of the lectures, Tuesday lectures, we'll ask him to, share his knowledge in one of the Tuesday lecture. Okay?
Yeah. Okay. Yeah.
Yeah. Okay. So basically, what we are talking is here structures having columns, beams, rigid joints, and column spacings can be something like 6 to 9 meters, because anything less than that, you'll find it's too much interference at the foundation. So when you go for 6 to 9 meters, again, you'll need massive thickness for the slab. So you'll go with secondary beams, and you'll ensure the secondary beams are can reduce the spans to around 4 to 4.5 meters. So the moment is 4 to 4.5 meters, you can easily complete the slabs by using 150 millimeter thick reinforced concrete. And that way you can save a lot of steel, because you have less concrete, means you need less steel to control cracking. You have a lot of steel, lot of thick concrete, then you need a lot of steel to control cracking. So always it's cheaper to go with second beams and slab in Sri Lankan context, because our labor is still not dominating. Costs are still dominated by the cost of the materials. So any country where the cost of the material dominates the construction cost, then it is cheaper to go for more labor intensive thin slabs than using thick slabs, which needs very little labor. So that is the theory. But in the countries where the labor is so expensive, anything extra to save material will not become worthwhile, because saving on time and saving on materials is not saving in time is important, but not saving in materials, because the labor costs are so high. Right. So basically, you can go up to about 20 floors, but one of the drawbacks of this system is, as you come down, you can see the bending moment increases on the structure due to lateral loads. And these heavy bending moments might need stronger sections as columns, and also stronger sections as beams. So if you are needing bigger beams in this area, the bottom area, what is the problem? The problem is, when you are doing a build structure, you always like to standardize the form. So the moment you try to standardize, one of the requirements is never change the sizes as you go up, change the reinforcement. Never change the sizes, but change the reinforcement. So basically, if you have the frame only, no shear walls, you can go up to about 20 floors. But the problem is, you might need bigger beams in these areas. And columns is not a major problem, because people generally accept that every 10 floors, you might have a different section for the column. It is accepted. But if you are going to say, I'm going to change the size of the beam as well, then there will be many unhappy contractors. So they say, I'm going to have, my main problem is the slab, I'm going to have a proprietary system. Once I order it, I can't change the size of the beam. So the good practice is, select a reasonable size for the beam and then adopt it everywhere in the building. But don't select something like, once you select the size, don't select something like 500 millimeter deep beams. So generally in tall buildings, you will go for something like 600 millimeter deep beams. The reason is, when you have 600, you might find you can carry a bending moment as low as 30 or 40 kilonewton meters to 250, 300 kilonewton meters using the same section. So because of that reason, always think of using a minimum thickness, minimum depth of 600 millimeter. But if you want, you can define that as the maximum depth as well, because we don't want anything less than 600, and at the same time, we don't want anything more than 600. Anything more than 600 means 800 means 200 millimeters extra needed for to keep the headroom. So instead of 3.6 meters, now we are using 3.8 meters. And every floor, you're adding 200 millimeters or 20 centimeters. So if you are doing a 40-story building, 40 into 0.2 is 8 meters, and you can easily have two more floors. Then the developer might say, okay, so I mean, I have, because of your decision, I had to use what do you call more facade material, which is sufficient for 2 floors height, and I had to use more cladding material and so on. So try and keep the floor-to-floor heights at reasonable levels, and the reasonable levels can be something like 3.6 to 3.7 meters. But don't have a huge range like 2.4 meters up to 4.2 meters. Don't try to have huge range for floor-to-floor heights, because the cladding also part and parcel of the cost. So if more height, more cost for cladding. So due to need of beam, column junction, so basically it's particularly suitable for reinforced concrete buildings. So as you come down, now the whole moment due to lateral loads acting on the low floor columns and beams, so you might need, you can have to have large columns, but you might need to have large beams as well. Right. Now, just one moment. Then we can also have another system which was very popular in the Eastern Bloc countries, and that is use of infill walls to resist lateral loads, And you might ask, how do you design this type of systems? And the design methods are given in the book by Smith and Cole, and there's a very good book for tall building design by Smith and Cole. And try and find a copy of that. It's a very complicated book with loads of mathematics. But you don't have to go through all the mathematics, but just try and read, because I also have used a lot of material from that book. It's one of the finest books ever written, but both authors are dead now. They are no longer living, but it's a fantastic book. But again, you have to keep in mind when you are reading, it covers the way that the theory has evolved before the computers. So because of that, there are a lot of theories in that book that cover the fundamentals of tall building behavior fundamentals. But these days, now we are going far beyond what is in the book, because today we have computers, we have software, and we can model the same structure with finite element method. Because we can model the same structure with finite element method, we can see the behavior ourselves. Right? We don't need theory to determine the behavior. We can make a model and see it ourselves. But to know whether the results given by the computer is correct or wrong, what do you need? you need some knowledge and you need to know what the theory says. So to get that knowledge, just glance through the theory and see what they have done and see the summaries and see whether you can get a reasonable idea about the behavior, but don't try to understand all the mathematics in that book, because that book has been written before the time that computers became so widely available, because it was published in 1990 or something, or 1992, which means the time that people were having. Do you know the strength of the computer, a reasonably good computer in 1992, 1991? It was only a 486 machines. Not even the Pentiums, no what do you call i3 or i5 or i7 series. So those days in 1992, laptop of yours would have been something like a supercomputer. But today things have changed a lot. But still, you have to always keep in mind, garbage in, garbage out, which means unless you get an idea about the behavior by going through the mathematics, then it's hard to say whether you have used the correct method for modeling, or also whether you are getting the correct answers. So basically, when you look at these structures where you have beams and columns, and then we infill them with masonry, and we expect that masonry to carry all the lateral loads. But what can go wrong? So basically, you can't change any of the partition walls as you like. So that is the first thing. What is the next thing? You can't change the partition walls as you like, because they are there for a purpose. And secondly, you must know the properties of the infill material. You must know the properties of the infill material. So for that, you will have to make models, load it, get the basic properties, predict the behavior, and so on. And for that, again, there's a research paper published on engineer transactions, IESL transactions, 1998. And because it was on transactions, you can download it on internet, and that particular paper won Professor E. Pereira Award for the best paper. In 1998, there's a paper published in 1998, IESL transactions. So just look at that paper where the properties of Sri Lankan bricks have been used to see the kind of lateral loads that can be resisted by the masonry, where for the analysis purposes we can replace the whole masonry panel by using equivalent diagonal members. So this is covered under Smith and Cole's book, and also there's a paper that we did using some of the information where we adopted the theory for Sri Lankan brick properties. So we have the bricks made with hand molded techniques in Sri Lanka, and we have certain properties, and then we have mapped those properties to a research study, and then we have come up with conclusions. So just make it a point to read that paper. So basically, if you have only the frame, it's unbraced. The moment you fill it with solid material, it's braced. So simple theory. Because these masonry panels can be removed without warning, what is said is, don't use these as the primary lateral load resistance system. Always have a moment resisting system using the beams and column junctions. But if you want additional strength, you can rely on these additional things rather than increasing the size of columns and beams. So if somebody asks, I like to have more strength, more safety, then what you do is, you will make the size of the columns and beams bigger and make it stronger. But it's not necessary if you have good partition systems, regular partition systems. Then basically you can model those and determine the kind of additional strength that can be given by the frames, and then you can add the lateral load resistance of the frame and lateral load resistance of the infield panels, so that once you combine both, you have a factor of safety well over 2.5 or close to 3. I told you that the system has been used in Russia in big way, because when Russia was a socialist country, some 30 years ago, or more than 30 years ago, they had a policy. The policy is each and every citizen should be given a house. But they did not have enough material and so on, so they went for very simple systems. And then, this mainly happened in the South Bloc countries like Armenia and Azerbaijan, those countries. So what happened was, there's a big Armenian earthquake in 1991. What happened? All these masonry structures collapsed because the bearings were not enough. They have just kept it at the edge. So when the wall started shaking, the slab panels collapsed and the buildings were destroyed. Huge number of people were killed. I have some thousands of people, like 20, 40, 50,000 people were killed. And if you type on internet, Armenian earthquake in Armenia, it says 2 earthquakes hit Armenia on 7 December 1988, killing 60,000 people and destroying nearly 500,000 buildings. 2 tremors only minutes apart were measured 6.9 and 5.8 in magnitude and were felt as far away as Georgia, Turkey, and Iran. So what happened was, it simply flattened the 2 cities, major cities in Armenia. And then you'll ask, where's Armenia? Armenia is, as a lower latitude, and they were all Russian bloc countries. Some after the Second World War, and after 1990 they all got freedom, and today they are separate countries. And you would have also seen that Armenians and Azerbaijan people have been fighting each other So basically, what you have to see is, if you have bad construction, poor structural forms, a structure collapses in an earthquake, the damage is 60,000 people killed and 500,000 houses destroyed. So these are true events. And from these true events, you can see there's a lot of damage that you can expect when you do not have proper systems. And the problem with masonry is sometimes you tend to say not to tie masonry properly. And when you don't tie masonry properly, you can run into enormous problems. So basically, when subjected to lateral loads, the infill behaves like a strut. So basically, mainly the infill panel goes into compression, and it will act like a compression member, and then there can be some kind of cracks occurring due to the deformation of the panel, and these cracks occur due to shear failure or tensile failure. So all those failures are covered in sufficient detail in that paper. And if you want more information, always refer the book by Alex Cole and Smith and Cole. I think the first house is Alex Smith and Smith and Cole. Just one moment. The name of the book is Tall Buildings by Smith and Cole. Yes, it's called Brian Smith, Brian Stratford Smith and Alex Cole. Alex Cole and Brian Stratford Smith. So that is the book. So it's one very good book, and copies are available in the libraries, and you might find sometimes even some soft copies somewhere. And one day the other, read the. Then the main challenge in infill panels is the quality of the masonry used. Quality of the masonry used. And then, now, if you can rely on these infill materials to carry all the lateral loads, the frames can be designed primarily to carry vertical loads. But there are a few checks that you should do to make sure there cannot be any local failures in beams and columns. And it is strongly recommended, when you do not have shear walls, design the frame as unbraced, but you can improve the strength by having infill panels. So shear wall structures. Shear walls are concrete walls, not like infill walls. You cannot remove the concrete walls easily because it's hard to remove them. And because of that reason, we use shear walls a lot in our buildings, and shear walls can be made out of concrete, and higher the strength of concrete, higher the elastic modulus, lower the deflection. And that is the main advantage of using shear walls, because sometimes if you find that it's difficult to control the accelerations, wind-induced accelerations and so on, you might use higher strength concrete for the shear wall system. but that will all depend on the height of the building and so on. So this is a typical example, and sometimes these days we don't use these kind of extra columns at the corners, but nothing says that you cannot use it, can use it, but you have to make sure that correct strength materials have been used so that you can get the appropriate elastic modulus, and that will help you to assess, make an assessment of the wind-induced acceleration and the drift. The drift will come from the computer modeling, and wind-induced acceleration will come with all the other parameters plus the properties of the building like natural frequency. So when you have shear walls, you have so many floors, so many lifts, shear walls, then you have a strong structure. Then in modeling, if you want, you can ignore the frames and do the design, but I always advise, because we have software readily available with us, just do a simple model. Just do a simple model and see. The interaction between the frame and the wall. And I showed you the interaction between frame and the wall earlier, but always do proper modeling, because early days when they see a lot of shear walls out of concrete, they simply design the vertical frame only to carry the frames only to carry the vertical loads, whereas all the shear walls have been designed to carry the lateral loads and part of the vertical loads. That is the way it happened, but you have to always keep in mind you can't have high strength materials and control the drift very easily. So if you want, you can use high strength materials only for the wall. Again, when you are talking about high strength materials, you will not go for 28 days strength, because knowing very well, because you have added 15% or more fly ash, these concrete walls are going to gain strength over a long period of time. And as it gains strength, your building will become stronger and stronger, no movements, and then you can say that I have designed a wonderful building because I did not rely on 28 days strength, I relied on 90 days strength also. So now the time is about 8:25, because you know these shear wall structures in also a lot of work like proportionate systems and done from non-twisting systems, twisting systems, non-proportionate systems, so many different systems to be learned. So we have only about few minutes more. So if you want, I can take 1 or 2 questions and wind up the lecture so that we can actually continue this lecture, because this is a very important part. And unless you understand this, there's no point in understanding how to do computer programs, because computer programs can actually make you destroy your career by giving you wrong answers because you did not understand the behavior. So you just plugged in some numbers and got some numbers out, and they are totally wrong. And you can end up with serious trouble when you don't understand how the structures behave. So we can spend few days, we learn it properly and move forward. So, Engineer Kamala, how many questions we have? Chat box, I see one.
Yeah, chat box only one. Chat box only one.
Yeah. So that is about ties. Yeah, that is about ties. I mean, in BS 8110, you have ties. The same rules are available in Eurocode as well. So simply really check. And if you use very similar rules, they are very similar to British codes. So the Thai requirements are there in Eurocode. And if you want to understand it, I think it is covered well in McGinley's book. And I can't remember whether it's covered fully in the book by Musli and Banji. But in McGinley's book, I think it's covered. So basically, I mean, just if you are familiar with Bayes 8110 and you are design ties, then simply, you don't have to do many calculations. I mean, it's very similar equations. You can adopt the tie. That's the only question we have. Anybody else having questions? Please, you can raise.
Yeah, there was one raised hand. Engineer Premathilaka.
Yeah. Who is that? Yeah. What is the question, please?
Yeah, Engineer Premathilaka, you can ask that. Be silent.
Engineer Premathilaka, would you like to unmute and ask the question?
We'll proceed.
Engineer Premathilaka.
Yeah. Okay.
And there's another comment on saying that Ravi's knowledge on admixtures is marvelous. We can invite him. And by whom is that?
Samad.
Yes, Samad. Yes. So basically, I mean, he's superb. His knowledge is superb. And if you want even things like beyond the codes, you say you need 120 megapascal concrete where the code allows you only 105 megapascal. I'm talking in terms of cube strength. You can always refer to the Eurocode and get the cylinder strength. But I'm talking in terms of cube strength. And if you want something like 120 megapascal or 140 megapascal concrete, then just ask him and he will manufacture very special admixtures that will allow you to reach very high strengths. Any other question?
No more questions. Shall we wind up?
Yeah, we'll wind up and we can. What is the?
I will call Engineer Trimavitan to deliver the vote of thanks.
Yeah. Okay.
Yeah. Good evening, everyone. So I would like to use this opportunity to give vote of thanks. First of all, the Professor Jai Singh. Always you are encouraging everyone. So I can remember my university life as well. So the today lecture actually the continuation. So I hope that it should continue for the next session as well, because there are a lot of things to learn. For the participants. So I hope that the next lecture will be the most important lecture that you are going to cover. Thank you, Professor, so your time and your valuable effort. So thank you very much. Have a very good evening today. And so we appreciate your the contribution to the society and for us. So encouraging us and giving the sharing your knowledge. Thank you very much. Excellent, Professor. So
yeah, okay,
I would like to.
Much, thank you very much, Trimavitan.
Yeah, you're welcome, sir. So in the meantime, so we give our thanks to IESL for hosting this event, as well as this organizing subcommittee, and all the participants who participated this lecture. And without you, actually, we can't make this success. Right. Thank you very much. Have a very good evening to all of you. Thank you. So we'll see you with the next lecture. Thank you. Good evening, everyone.
Thank you very much.
Thank you. Good night. Good night.
Good night.